According to our best theories, the universe shouldn't exist. So where did all the antimatter go? When the Big Bang erupted, it should have forged equal amounts of two kinds of stuff, matter and antimatter. Think of them as cosmic twins, almost identical in every way, but with opposite electrical charges. The electron has its positron, the proton has its antiproton. But there's a cosmic catch. Whenever a particle of matter meets its antimatter counterpart, they don't just high-five. They annihilate each other in a spectacular burst of pure energy, leaving nothing but light behind. It's the universe's most perfect disappearing act. If the Big Bang really did create them in equal measure, then every single particle should have found its twin and vanished. The result would be a vast, empty cosmos filled with nothing but leftover energy. No planets, no stars, no life. No, you're sitting there, wondering why you exist. And yet here we are. We look out into space and see a universe made almost entirely of matter. Antimatter is incredibly rare, only popping up in fleeting moments, like in high-energy particle collisions or cosmic ray interactions. This profound imbalance is the reason anything exists at all. It's one of the biggest, most fundamental puzzles in all of physics. Scientists, acting like cosmic detectives, have a lineup of prime suspects to explain this grand disappearing act. Each theory offers a tantalizing clue as to how matter won the ultimate cosmic battle for survival. First on the list is a phenomenon known as CP violation. The C stands for charge conjugation, which is like swapping a particle for its antiparticle. The P stands for parity, which is like looking at its mirror image. For a long time, physicists thought that the laws of physics would be the same if you did both swaps at once, a concept called CP symmetry. This would mean matter and antimatter are perfect mirror images in their behavior. However, experiments have shown this isn't entirely true. Some particles and their antiparticles don't decay in exactly the same way. This slight, subtle asymmetry, this tiny crack in the mirror, might have been just enough. Over billions and billions of interactions in the hot, dense early universe, this small bias could have accumulated, leaving behind one matter particle for every billion pairs that annihilated. It's a small leftover, but in a universe of countless particles, it's enough to build everything we see. Another leading suspect involves a ghostly, elusive particle, the neutrino. Neutrinos are incredibly light, barely interact with anything, and come in both matter and antimatter versions. The theory of leptogenesis suggests that very early in the universe, heavy, unstable types of neutrinos existed. As these primordial neutrinos decayed, they might have done so asymmetrically, producing slightly more leptons-like electrons than antileptons. This imbalance in the lepton family could have then been transferred to the baryons, the family of particles that includes protons and neutrons, through other physical processes. Essentially, the neutrinos might have tipped the cosmic scales in favor of matter right from the start, setting the stage for the universe we inhabit today. Proving this requires observing a specific behavior where neutrinos can switch their identity, a process that experiments around the world are furiously searching for. Of course, there's always the most exciting possibility: unknown physics. The standard model of particle physics is our best description of the fundamental particles and forces, but we know it's incomplete. It can't explain dark matter, dark energy, or the full extent of the matter-antimatter asymmetry. There could be entirely new forces of nature or undiscovered particles that played a crucial role in the universe's first moments. Perhaps there are other heavier particles that decay preferentially into matter. Or maybe antimatter wasn't destroyed but was somehow separated, pushed into a corner of the universe we can't observe, forming anti-galaxies in a distant, isolated realm. While most evidence points against large pockets of antimatter, the possibility of new physics remains a powerful motivator for exploration and discovery. To hunt for answers, scientists are running some of the most sophisticated experiments ever conceived. At CERN, the Large Hadron Collider LHC smashes protons together at nearly the speed of light, recreating the energy-packed conditions of the early universe. The LHCb experiment, in particular, is designed to study the subtle differences between matter and antimatter particles, specifically those containing beauty quarks. By precisely measuring their decay, scientists can test the limits of CP violation and search for deviations from the standard Model S predictions. Every collision provides a snapshot of the fundamental laws of nature, offering clues about why matter gained the upper hand. Meanwhile, other experiments focus on the neutrino. In Japan, the T2K Tokaitu Kamioka experiment shoots a beam of neutrinos through 195 kilometers of Earth to a massive underground detector. By seeing how many neutrinos change their flavor along the journey, scientists can look for differences in the behavior of neutrinos versus antineutrinos. Similarly, the NOVA experiment in the United States sends a neutrino beam from Illinois to Minnesota for the same purpose. These long baseline neutrino experiments are at the forefront of the search for the asymmetry that could have saved our universe from annihilation. Each piece of data, each observed event, helps us piece together the story of our own existence. This mystery is not just an abstract academic question. It's the reason anything exists. If matter and antimatter had been perfectly balanced, our universe would be an empty void of light. Instead, a tiny, almost imperceptible flaw in the cosmic rulebook allowed for a universe of stars, galaxies, and life to emerge. The search for the missing antimatter is ultimately a search for our own origin story, written in the language of fundamental physics. It's a reminder that we are here because of a profound and beautiful imbalance at the very heart of reality. If matter and antimatter had been perfectly symmetrical, the story of the cosmos would have ended before it even began. That 1 in billion survival rate is the reason we have a story to tell at all. The quest to understand why is a testament to our drive to know where we came from and our place in the cosmos. And with every particle smashed and every neutrino detected, we get one step closer to solving one of the deepest mysteries of all: why we are here.
Stay curious.